Okay, we can start. Welcome everybody. Third lecture. There is, by the way, only one person officially attending the course in the classroom. Everybody is online. So today is lecture 3 on thunderstorms. Last time I said hurricanes, but hurricanes is tomorrow. So in the last lecture, well, first lecture, are there any questions from previous lectures? Online, in person, I see there is none. Anybody online has questions from previous lectures? Okay, I also don't see any. So in the previous lecture, we discussed these mid-latitude cyclones or extratropical cyclones, and you can see there are many storms associated with them. Particularly with this cold front that we discussed in great details in the previous lecture. And here is a typical storm, not associated with cyclone. This one is isolated. These types of storm clouds are known as cumulonimbus. And they're also known as anvil clouds because this whole structure resembles an anvil, as you can see, that the smithing people used. So there is some sort of resemblance. And this cloud is quite big. The horizontal dimensions are 10, 20, 30 kilometers, sometimes even more, 50, 60. Vertical dimensions are the pretty much entire depth of the troposphere, minus first kilometer or so, because that's usually condensation level there. So they are 10 kilometers deep or so. Now, there are basically 3 types of thunderstorms when we talk about isolated thunderstorms. And then, so that is what I will talk in this first 45 minutes. And then in the second 45 minutes, I'll talk, if there is time, about squall lines, which are lines of thunderstorms. So isolated thunderstorms come as single cells, multicells, and supercells. And the main distinction between these 3 is really associated with environmental winds. If environmental winds have very weak shear in terms of both speed and direction, that means wind speed as well as wind direction are not changing profoundly with height, but we do have some convection, then it's likely we have single cell thunderstorms. If wind speed is changing with height profoundly, but not necessarily wind direction, and of course we have strong convection, we might end up with multicell. And here you can already see multiple cells embedded in this cloud. And then the case when both speed and direction are changing with height, as well as strong convection, we might have supercell, which is the strongest of all thunderstorms on this planet. So here is an example of a single cell thunderstorm, which are the weakest thunderstorms. You see, it's still vertical, very well developed cloud. It has updraft and it has downdraft right next to it. Here is an example of multicell cloud, much bigger. You can see anvil spreading in that direction. You will see these are overshooting tops, and you can see new cell, young cloud developing on this flank of an older cloud. And finally, we can have supercells, which are the strongest of all clouds on this planet Earth, associated with most tornadoes, particularly strong tornadoes, associated with large hail, very strong downdrafts, and so on. So, okay. So that's the introduction to this lecture in terms of pictures and slides. So now we can go a little bit on Blackboard, and I can just disconnect this from Amazon. What is that? Screen. Oh, okay. Oh, yes. Or you can do that.
Like this, huh?
Yeah, yeah. So now we can discuss these on the blackboard and how they form, evolve, and so on. I am recording, guys. So first I would like to talk about single cells, which are the simplest and weakest of all thunderstorms. So generally, they have three stages of development. If this is the Earth's surface, then this is height Z. The first stage of single cell is actually a regular cumulus cloud. Cumulus clouds, you will remember from first lecture, are clouds that are thicker than wider. Generally, if this is the diameter of the cloud, then the height of a pre-storm cumulus is approximately 1.5 diameter. And these are known as cumulus mediocris to cumulus congestus. But you don't necessarily, I'm not going to insist, you know. So, cumulus mediocris is a medium-sized cumulus cloud, whereas cumulus congestus is very well-developed cumulus cloud. And there is also cumulus humilis, which is very weakly developed cumulus cloud, but not so much important. Now, these single-cell thunderstorms typically develop in the late afternoon. There are several reasons. One of them is that the Earth's surface is warmest in the late afternoon because the sun was heating it throughout the day. So the possibility of convection is therefore strong in the afternoon. The second reason is one day when you wake up on a nice and sunny day, observe clouds, sky, and you will see many weak cumulus clouds, cumulus mediocris, cumulus humilis. They form and disappear, But their death is actually very important for the next generation of clouds. As they disappear, they make atmosphere more moist, so that the next generation of clouds can last longer. Because what is mostly killing the clouds? If you have this cloud over here, this is cloud, this is the rest of the atmosphere. Entrainment of dry air is what destroys clouds. This process is known as entrainment. Now, clear entrainment for people online that cannot really see. Now, clearly, if the atmosphere around the cloud is very dry, then when you bring in that dry air into the cloud, it promotes evaporation, and that's what kills the cloud. However, if the outside atmosphere is already moist, then that air is not as efficient at promoting evaporation as a very dry air. So the first stage of single cell thunderstorm is this cumulus cloud that grows and becomes cumulus congestus. What is the dominant characteristic of first stage of thunderstorm? The whole cloud is abrupt. Okay, that's the important thing to remember. So cumulus congestus, or the first stage of a thunderstorm, single cell thunderstorm, is that entire cloud is an abrupt. At this time, we don't have precipitation. These abrupts can be order of 5-10 meters per second, not more than that usually. In the case of single cell thunderstorm, sometimes even less. So the top of the cloud is several kilometers into the atmosphere, maybe 8, 9, 7, something like that, okay? So that's the first stage of a single cell thunderstorm. Now, what would be the second stage? Well, from here, the system transforms into mature, we would say, thunderstorm. So early stage, second stage is mature thunderstorm. In this stage, Cloud usually has this shape. I'll explain soon why. But what is the dominant characteristic of mature stage? In mature stage, cloud has both updraft and downdraft. So part of the cloud is updraft and part of downdraft. And at this stage, if there is precipitation, it reaches the surface. It touches the surface, rain, usually. So you see, this kink on the top of the cloud is known as overshooting top. If the updraft is very strong, it can penetrate into the stratosphere a little bit, and then you get, but it cannot go far into the stratosphere because you remember from the first lecture, the stratosphere is stable, very, very stable. Temperature increases with height. So you get these downdrafts here and then spreading like so. As in the updraft, we have formation of precipitation. As I said in the first lecture, unfortunately, I don't have time to talk about microphysics processes because that requires several lectures. But precipitation forms in the updraft first as a liquid water, and then maybe it converts into ice. And then that the liquid water plus ice are together known as hydrometeors. And they start falling. And as they fall, some of them evaporate and melt, decreasing the temperature of the downdraft, and we have downdraft that reaches the surface. So if you would measure, let's say somewhere here is 0 degrees Celsius. And let's say here 0 degrees Celsius continues. What do you think, one person? Is temperature in the downdraft lower or higher than 0? Or people online can also speak. In other words, when I plot this, should I plot it like that or should I go up? Up? That would mean downdraft is warmer than the other. What do you think online? If you can see this, by the way. It seems to me you can. Anyways.
Down.
And then in updraft, it should go up, like so. Because in updraft, you have condensation, and condensation releases latent heat. So updraft is warmer because of condensation. Downdraft is colder because of melting and evaporation of ice and liquid water, respectively. Does that make sense? Now, single cell thunderstorms are also weak because this downdraft is strongly interacting with updraft. Quite often, this downdraft forms a bob, therefore reducing the intensity of the updraft. Okay? And then when this cold downdraft hits the surface, it spreads radially in all directions. Now, we rarely have very strong downdrafts from single cell thunderstorms, rarely. So this is not some strong downburst that hits the surface and destroys something. It's a relatively mild downdraft that hits the surface, but it spreads. It spreads like so. Yes, you have a question?
No, I was asking, so the profile is the same, but it changes the intensity compared to the downburst?
Yes, so every thunderstorm, every single time you see a rain, there has to be downburst associated with the rain. Now, how do we say this is downburst or not? Just by intensity.
Oh, so there's a threshold.
There is a threshold, but it's not very well defined. Threshold is 10 meters per second. This speed that you, but where, you know, it's not the same when you measure. So it's really subjective, to be honest. If you have strong winds, you say, wow, this is downburst. Because where do you measure 10 meters? per second, at 10 meter height, 20 meter height, 30 meter height, so it's just subjective quite often. Now, there are in research, there are some criteria that people propose. 10 meters per second is what Fujita proposed, but it's not enough. You have to have some other things satisfied, which I will talk about in lecture on hazards. Now, because I will erase this part now. Remember, we said that in the case of single cell thunderstorms, wind speed shear is very weak. So that means that, of course, wind is zero on the surface, but maybe winds are not changing in height profoundly. Something like this. Not exactly constant, but pretty constant in height. As we will see, particularly when I move to multicell thunderstorms, this weak shear enables outflow to move far away from the parent storm. So you see, as this outflow is advancing, we have updraft somewhere here. And even if this updraft generates new clouds, they are far away from the parent storm, so they will not connect with the parent storm. So you might get series of single cell thunderstorms, but they do not connect. Okay? And that's also why actually single cell thunderstorms are not so easy to forecast. They are so isolated and they are small. Fortunately, quite often they don't produce very severe weather. Okay. And then the third stage of single cell thunderstorm is a dissipation stage. If this is the surface of the Earth, that means this whole cloud is just precipitation downward. Usually when you have precipitation everywhere, it's difficult to define lower base of the cloud. So it's not necessarily correct to plot some lower base because the cloud is dissipating usually from underneath up. So you just leave it like this. And this indicates there is a lot of precipitation. Sometimes there are some small pockets of updrafts that survive residual, but they cannot sustain the entire cloud. Okay?
Could you please
Entire cloud lasts thunderstorm around 30 minutes or so, 30, 45 minutes, not more than that. Any questions?
could you please turn the camera?
Yes.
If we have a downdraft, I mean, it was related to that profile.
Yes. Yeah.
How do you consider it constant, almost constant, let's say, if you have a downdraft?
How can this be constant if we have on?
Yeah.
This is environmental winds. This is like, let's say, from X, Y. Okay? You have this cloud somewhere over here. And then what I'm describing here are large-scale winds that blow over entire Mediterranean, entire Italy. So what we would say, this cloud is embedded in these winds.
Okay.
And these winds have this vertical profile, which is pretty, it has to have some shear close to the surface, but then it's pretty constant height.
Oh, okay. Okay.
Does that make sense?
Yeah.
These are also, therefore, if I go back to this, because this cloud pops up here, and maybe another cloud here, these are also known as air mass thunderstorms. They just pop up out of nowhere. But that's just label. Doesn't, I mean, different name.
Excuse me, can you hear me?
Can you please?
Yes.
When we speak about gust fronts,
Yes.
we are referring to this type of fronts or?
Yeah, this is also, so any gust front by some sort of definition is the forward edge of spreading outflow. Actually, it's not the outflow doesn't have to be intense and you get some downburst. But any forward edge, what I plotted here of a spreading outflow is called gust front. So we would say new cells develop along the gust front. In other words, along the leading edge of outflow.
Excuse me, can you hear me?
Any question, folks? I see something in chat.
Excuse me, can you hear me?
Could you please turn the camera so we can see the third stage? Okay, I erased it. Third stage is just precipitation and dissipation. Just whole cloud is downdraft, and there is no updraft to sustain further development of this single cell. But I will try to rotate this camera a little bit better. But then I destroy the other part of the blackboard. Okay, when I move to this one, I'll rotate camera. Okay. So this was single cell thunderstorms. Now we have multi-cell thunderstorms, which really are a series of single cells, basically. So let's say here is the surface of the Earth. Again, this is the height, Z. And maybe we have cloud like so, okay? Now, if the whole system is moving, let's say, in this direction, and we have storm relative winds coming into the storm, like so, then we have one updraft over here, another updraft over here, like so. Here is already downdraft that is forming. And here is precipitation reaching the surface. So in this type of multicellular thunderstorm, we could say this was cell 1, the very first cell that formed, and now it's just dissipating. This perhaps was cell 2 that formed after this one. This is cell 3, cell 4, and cell 5. Okay, so you can see, we will soon discuss what is causing this updraft here, but let's just assume there is updraft here. You see cell 5 is in the early stage, what we would call, with respect to nomenclature we used in single cell thunderstorms. Cell 5 is early stage. Cell 4 is also early stage, but very late early stage, close to be mature. Cell 3 is mature. There is updraft, there is also downdraft. And cells 2 and 1 are in dissipation stage. Okay? And there is precipitation over here in the part of the cloud associated with mature and dissipation cells. Now, when this downdraft hits the surface, once again, it spreads. But in the case of a multicell cloud, it doesn't spread far away from the cloud. So the updraft that creates new cells is connected to the rest of the cloud. And you see the new one is kind of attached to the cloud. And this environment is associated with rather strong wind speed shear. Okay, so winds are profoundly changing with height. So there are two ways now to explain this. One way is to say winds at higher elevations are stronger at bottom, so they push the upper part of the cloud more than this. So this catches with the downward, okay? Because wind here is weak, wind here is strong, so this is moved more than this. Okay? Another way is to visualize here that there is vorticity, like so. Wind is changing the time forming this type of vorticity. So you can see if there is vorticity here, like so, they kill each other over here, but they amplify each other over here. Vorticity is defined as nabla cross V, whereas nabla is, well, nabla is nabla, vector differential operator, V is wind speed. So if you have U winds that are changing with height like so, you can demonstrate there is this vorticity. So let's say we have a wind V that is U component 0, 0. Then you will get omega I, J, K, delta, delta X, delta, delta Y, delta, delta Z, U, 0, 0. I'm going, I mean, at the end of the day, this is graduate level course, so I'm going a little bit fast in this, but if you now calculate omega, you will see delta U, delta Z survives, which means delta U, delta Z is causing vorticity. And it is causing vorticity in the J direction, which is direction into the blackboard, which you can see this is direction into the blackboard. So this is vorticity associated with environmental winds, winds that exist in the atmosphere with this storm. And you can see on this part of the outflow, vorticity generated by the outflow and vorticity generated by environmental winds kill each other. Whereas on the other part over here, they couple, creating much stronger down updraft here rather than here. Okay? Now, of course, situation is usually not so simple. It's not necessarily that V and W are 0, but this is just to demonstrate the concept. Yes.
The velocity profile is the relative profile or is an absolute velocity? The one that you are talking?
No, this is absolute. Yeah.
So it's not like a seen from the storm.
So this is not a simple storm. This is absolute profile. Yeah. So wind shear is like so. S. I don't want to actually for people online to confuse them with shear. For you that you maybe know this. Okay? So that's multicell thunderstorm. And you can see it's just series of cells. This storm lasts much longer, maybe 1 hour, 1 hour, 15, 20 minutes, 1.5 hours. And it's capable of producing much stronger downbursts, sometimes, very rarely, but sometimes tornadoes and sometimes, but rarely hail. But these are the most common types of thunderstorms actually in mid-latitudes. They are more common, research suggests, than single cell downbursts, single cell thunderstorms, okay? Now you might say, but why do you have vorticity over here in the outflow? For that, I will write equation that takes 1 lecture to derive. It's not an easy equation. Yeah. You see, over here, we had equation of what is vorticity. But you can also derive equation what is resulting in the change of vorticity. So that would be d omega dt. And here I am neglecting planetary vorticity associated with the Coriolis force. So of course, this can be local change plus advection. That goes without saying. But this is equal omega dot nabla times V. You don't have to memorize this equation. I did it so many times, I know it. Plus nabla rho cross nabla P divided by rho squared and plus nabla cross F, where this F is some frictional force. This is, by the way, stretching and tilting over this. This explains why ballerina spins faster when brings her arm closer to her body and so on. But this is Baroclinic generation of vorticity. You see, if this is the surface of the Earth, and this is height Z, and you have outflow that is spreading like so, just zoom in on that part of the outflow close to the storm. Then general pressure differences between outflow and surrounding atmosphere are not large. Maybe this is how pressure is changing. It's not straight, but I want to demonstrate the point, okay? So here is P minus 1, P minus 2. But this is cold air, this is warm. Density differences are larger. Again, not this. So you see another row cross sorry, it should go like this. Nabla rho cross nabla P. So this is pressure. Yes, no, I was right. So this is rho minus 1, rho minus 2. So you get nabla rho like so, and you get nabla P like so. And nabla rho cross nabla P, you get vorticity like so. I went fast with this, but pressure is increasing with height, decreasing with height. Sorry, as we discussed previously. This is cold air, this is warm air. So density lines are not aligned with pressure lines. So this is nabla rho, this is nabla P. When I cross these two, I get vorticity like this. So one more time. If this is the gust front, what he said, forward edge of an outflow, you get vorticity developed like so. Thanks to this equation that I didn't derive, you can come to my office or check literature that I provided. But you see this term over here, which is called baroclinic source of vorticity, results through this, what I said, because pressure lines are pretty constant, parallel to the ground, whereas density lines are inclined. And you get this type of vorticity. So, for example, when you are doing wind tunnel experiments, then in impinging jets, then you miss this term. So vorticity that you generate is lacking this baroclinic source. Okay. This might have been a little bit confusing, but it's actually quite simple once you check this on your own. Okay. Very boring here. Any questions? The camera is out of focus. The figure and text are pretty blurred. Bah. Let's see now. Is it better? Is it still blurred or fine? There is no answer, so I will assume it's fine. Not sure if it is my local. Okay. Any questions from people in the classroom. Well, now, yes.
The propagation of the gas flow, there are some formula to understand the velocity in which it is moving? This equation, what's some
Yes.
insight?
Yes, there is equation V is equal square root some constant K rho delta rho density differences divided by rho ambient, and maybe there is some constant here. But basically what I'm saying is that the velocity of front propagation depends on the density differences between, H. Height, yes. This is, I think, 0.2, some constant, square root of 2, sorry. Square root of 2 is 1. Yeah, so this is kind of square root of 2. This is density difference between cold and warm air, normalized by, I think, ambient, but double check, and H is this height.
Okay, so it's also a function of the temperature, no?
Yeah, that's the difference is temperature, because generally, what you will measure at weather stations are temperature and pressure, so you can plug it here. Yes.
Maybe it's a stupid question, but we say that it starts kind of turning.
Yes.
So the velocity that we're finding is just spreading, or is it kind of spinning
Ah,
velocity?
well, so if you have this outflow, because where is nabla rho cross nabla p? I mean, divided by rho squared, doesn't it? Where is this strongest? Well, at the edge. Because you don't have it here, you are constantly in cold air. So over here, you have velocity like so. I mean, again, close to the surface, it's weak. We will start it downwards. You get a nose-shaped profile. But this cross product is the biggest close to the edge of the gust front. So this is where you get rotation.
So that rotation is related to the rotation,
This to rotation.
not the velocity.
This is how fast this is progressing.
Oh,
How fast this is advancing. Velocity of the front.
So we can say that at the leading edge,
Yeah.
the velocity that I person will experience is the velocity of the front plus some velocity given to from the simulation.
Yeah, but velocity is usually higher here. It's not usually the highest here. Velocity here is higher because not everything goes into propagation. As you can see, it also rotates. So if you're asking me what is the relationship between VF and maybe this V maximum, I actually don't know. I don't know.
I'm just wondering what is the velocity at the leading edge of the front. So the front is propagating at here, but the high fires there will.
Exactly, they can move faster than that. Yeah, because here they move faster and then they swirl back. But the whole thing is propagating at velocity v. Now, the other thing is that I skipped here. Well, let me not skip it. Let me discuss it. There's only 5 more minutes. Is how multicell clouds have two ways of motion. One is actually moving in space, like a person walking in space, and another way is called propagation. Now I describe what it is. Let's say from horizontal cross section. So this is XY, and this is typical figure that is used to demonstrate that. Let's say this is how cloud looks like from top. And you saw I used number 1 to indicate the oldest cell. Number 2 was second to oldest. Let's say number 3 is mature, and number 4 is new cell in the early stage of growth. Now, let's assume this cloud is moving from west to east, like so. Now, clouds usually move, usually it means not always, but if you don't have better assessment, you can assume they move at a velocity average over the depth of the cloud. That's usually how they move, okay? So going back, this is the vertical of the cloud, velocity across, you take average of these vectorial direction and speed, and that's generally how they move, but not always. Now, this is how the cloud moves, but close to the surface, storm relative winds can be such that when viewed from the storm, wind is blowing at the surface from this direction. Okay? So this is not actual wind in the atmosphere. This is wind observed by a moving storm. So you're in a coordinate system moving by the storm, wind close to the surface might be this. Well, that means the new cell, number 5, might form here. Cell number 4 is here. Cell number 3 is here. Cell number 2 is here. Cell number 1 died. So our new cloud looks like this. And then storm relative winds are such that new cell number 6 is here, early stage. This one is now mature stage. This one is maybe mature or dissipation stage. Dissipation stage, and let's say number 2 as well as number 1 died. So you can see that there is also a component of this cloud moving in this direction. How the cloud moves physically in space is known as cell or cloud, no, not cloud, cell motion. And this form of advancement is known as propagation. Now, I am skipping it in this 12-hour course, but the direction of storm relative winds is very simple to determine from something I will write here, and then you can look on your own. I will not ask you that in the exam. Something known as hodograph. Hodograph is a tool that we use to assess how winds change with height in the atmosphere, and particularly useful when we study storms. So you can study it on your own. I was thinking hard, should I talk about it, but there is just not enough. Okay. So what you need to remember is that under certain conditions, storm relative winds might be quite different from the winds that are affecting the storm. So you can see if you sum up these two, you would end up that the whole storm is moving like that if you sum up these two together. And this is called storm or system motion. So storm motion is combination of cell motion and propagation. Propagation is basically cloud is disappearing on one side and appearing on other side, whereas this is literal motion through the atmosphere. Now it can happen that storm relative winds are opposite of cell motion, and then you would really get, let's say in this case, you have here, let's say here is 1, 2, let's just take 4, 3, 4. Imagine that the storm relative winds close to the surface are such, and the cell is moving in this direction. Then you would get that 1 is disappearing over here, and 2, 3, 4 new cell forming over here, 5. Okay, something like that. Okay, so that would be on storms. Well, not on storms, on single and multi-cell storms. So it's three. I can stop here, and then next lecture we'll talk about supercells, and if there is some time about squall lines. Any questions?
Read of course that there is an included prompt.
Yes.
Usually there are these kind of storms that are happening,
Yeah.
they're really strong. Usually.
Yes. Yes.
Is the usually it's a multi-cell or is it?
It's usually multi-cells are so associated with this. Yes. As we will see, a squall line is basically this multi-cell storm, but if you would extend it into the blackboard for 100 kilometers. Okay. So some of these are also squall lines, not all of them. Any question from online people? We are on a break, so feel free to ask or not ask. Maybe I open under. I will pause. Yes, that's a good point. So let me pause it. Recording. So we continue with supercell thunderstorms, which, as I said in the PowerPoints, is the most powerful type of thunderstorms on this planet. Now, in principle, they also quite often look like this. And you might say, okay, there is some updraft that spreads like so, and then there is some downdraft, and this is the surface of the Earth. In principle, yes. But the situation is much more complex. This is kind of vertical cross-section. Because winds are changing also direction with height, the storm has a lot of three-dimensionality, which we will discuss now in more details, because this is a little bit deceiving on how complicated the circulation is. So here is the graph that I practiced 5 hours this morning. Here is height Z. Okay. And here is the surface of the Earth.
Grazie.
And somewhere here, we have this thunderstorm, like so. Now, here, on this, here I will have projection of the flow if one is looking at the storm from this direction. And here I will have projection of the flow if you are looking sideways on this storm. Okay? So let's first look if I'm standing, so the storm is moving towards me and I'm looking right into it like so. And now I make a cross section here. What would the flow look like? Well, first, this is from photograph, from measurements, we know that storm relative winds in this direction are usually something like this. So the winds are constantly increasing in height, like so. So if I would project this storm over here, this is the bottom of the storm. It would look like so. This has to be clear. I'm looking at the storm like this, I make a cut. This is what I will see over there, okay? And the storm relative winds are blowing, the storm relative winds are persistently blowing like so. So you get, at the end of the day, inflow that might look like so, generally. Okay? So you have very strong updraft that also overshoots, creating this overshooting top in the stratosphere, tropical stratosphere, and then it descends like so. And part of it can also descend in this direction, but mostly like so. Okay? Is that clear what I plotted here? Now we plot storm relative winds if I look into the storm from here. Now, this is again height Z. In this case, storm relative winds are generally like so. So this would be, let's say, U of Z, but U storm relative, maybe, this is, no, sorry, this should better be called V of Z, storm relative, and this is U of Z, but storm relative, okay? So storm relative winds close to the surface are into the storm, and at the height, they are away from the storm. So if I project this storm over here, because I'm looking it from this direction, it's gonna look similar to this. So I have, look, strong inflow that tends to spread like so. Of course, always some of it goes a little bit like so, but predominantly it spreads like that. Now you have to put these two pictures together and maybe design three-dimensionally how the flow looks like. That's quite difficult actually in brain, so I think this representation is much better. So you see the inflow, but it's difficult, you see, would go like this and then up and then into the blackboard and spread like so. So it would go like this into the blackboard and then spread like so. Generally, that's how things look like. But as it is spreading, it's also going in the direction into the blackboard because the winds are persistently like so. So these are called supercells. Now, in supercells, we have two downdrafts. Okay? We had one downdraft in single cell and multicell clouds. In supercells, we have two downdrafts. One downdraft is here, producing rain, precipitation, and whatnot, in the forward part of the cloud. And this is known as forward flank downdraft. Okay? This is forward flank downdraft in the forward part of the cloud. Because you can see this very strong storm relative winds in the upper layer tend to move a lot of hydrometeors, a lot of rain and hail into the forward part of the cloud, and then it falls down from the cloud. In the back of the cloud, over here, and towards the south, because of this storm relative motion, we have another downdraft sometimes here, known as rear flank downdraft. So what I wrote here for online people is a rear flank downdraft. The rear flank downdraft, as the name suggests, forms in the rear of the cloud, forward flank downdraft forms in the forward part of the cloud. Forward flank downdraft has much more rain precipitation than the rear flank downdraft. What we plotted here is the so-called classic supercell. There are two sub-sections of supercells. One is called high precipitation supercell. High precipitation supercell generally forms when winds over here at high elevations are very low, so you get this precipitation concentrated quite close to the cloud, and you have low precipitation supercells that forms when these winds are actually very strong. So this is spread much further, and before falling to the ground, it evaporates this precipitation. But anyways, we will only discuss this classic supercell. Any questions? Yes.
From the central part where, I would say, exactly from where
Yeah.
there is no precipitation,
No.
unless it's not, I would say, the wind is a little bit low.
Yeah, so that's very good question. So we said that precipitation starts in the first part of this lecture. When we talked about single cells and multicells, precipitation generally starts forming in the updraft. But that's because updraft in these clouds are strong, but not crazy strong. They are 10, 15 meters per second. In supercells, updraft can be 20, 30 meters per second, even more. I think 50 something was maximum measured. At such high velocities, precipitation cannot form into the core, in the core of the updraft, but rather forms here at the top, and then it is spread by these high velocity winds at the high altitudes. So if you take a radar slice here, you actually get very little, very big radar echo in the updraft, because updraft is so strong. You get very strong echo next to the updraft where you have precipitation. Whereas in other types of clouds, you might have strong echo in the updraft because precipitation forms. Here, it just doesn't have time to form. That's how fast everything is transported to the top of the cloud. I will erase this if there are no questions online or here. Okay, I don't see any questions online either. Now, should I talk about more about supercells or switch to squad lines? I'm not sure. Well, let me say this, okay? Supercell clouds can rotate. The whole cloud can rotate. And let me explain just that in a few. Let's skip that, okay? Because if I start talking about it, I'm gonna end up. When I teach supercells in mesoscale meteorology, I have 3 lectures to supercells. So it's very difficult to summarize everything in 30 minutes, okay? So let me just say this, supercells can rotate and can split. Out of one cloud, you get 2 clouds. I'm not gonna ask you this clearly then on the exam because I'm not teaching it, but if supercells are something you are looking to research, then there is much, much more than what I said here. Particularly rotation, mesocyclone, splitting, you can study it on your own. What we covered here is the basic dynamic of flow in a supercell, okay, that I would like you to know for the exam. Yes?
In this area, which are more common? in the Mediterranean
Ah.
area.
Multicell storms, I think, are the most common, usually, maybe single cell. I don't know, I didn't now do climatological research somewhere here, but well, let's put it like this, for sure, it's not supercells. Because when you have supercell, most often you have extremely damaging hail, winds, lightning, I mean, a lot of lightning, sometimes tornadoes, and you don't see that quite often. So single cells and multi-cells in this region over here are done. Yes.
Quite often, thunderstorms are associated with the energy. The idea of energy. Say, oh, this thunderstorm has a lot of energy.
Yes. So that comes from, maybe you're talking about convective available potential energy.
Yeah.
So convective available potential energy is the buoyancy in the air, basically. So how much air is buoyant? If the air is very buoyant, so basically that means if you have a parcel of air that is much warmer than the surrounding, and particularly if it is much moister than the surrounding, we would say it has very high K, convective available potential energy. And that energy, so if you think about it, if you have very strong convection, so you have very strong updrafts. If you have very strong updrafts, eventually you will have very strong downdrafts. So strong updrafts, that's also one of the factors we use to predict how damaging winds might be, is examining how strong are updrafts in the cloud. Because the stronger the updraft, the stronger the downdraft. Because the stronger the updraft, you will have deeper cloud, which generates a lot of precipitation. And then you might have very strong evaporative cooling that will create very strong downdrafts. Now, energy in a thunderstorm, energy, if you calculate, is approximately 10 to 13 or so joules. And energy, this is famous, of a nuclear bomb thrown on Hiroshima was 10 to 11 joules. Or I forgot, or maybe this is 10 to 15, this is 10 to 13. I just know it's 2 orders of magnitude difference, I remember this. So you see, energy in a cloud, thunderstorm cloud, is at least 2 orders of magnitude larger than an atomic bomb. And all this, or most of it, comes from condensation. Because, as we discussed in the first lecture, water vapor has releases large amount of latent heat, 2,500,000 joules per kilogram. So you condense this 1 kilogram of water, this is how much energy you get. And then you can do estimates how much is condensed in a cloud, and you get these numbers. Of course, power is energy over time. So when the nuclear bomb explodes, it's in a millisecond. So you get huge power. That's why everything is destroyed. But cloud, as we just discussed, lasts 1-2 hours. So energy is dissipated over a much longer period of time, and the power of cloud is much weaker than the power of. But yeah. Any questions from online audience? Cool. Okay. Okay, so let's talk a little bit about squall lines. In your slides also, check your slides, I provided a radar. So what we discussed about supercells here was vertical cross-section. But in slides, I also showed what is the horizontal cross-section typically observed on a radar. screen, on the radar screen. Now I would like to talk about squall lines. So squall line, these are called mesoscale convective systems. There are several types of mesoscale convective systems. One of them are squall lines, another one are bow echoes. Another one is Zoom says, please confirm that your language of speaking is English. That just shows how good my English is. Because the computer didn't figure out, like, I don't know what this guy is talking about. Sounds like English, but I'm not sure. Anyways, mesoscale convective systems come in the form of squall lines, bow echoes, mesoscale convective complexes, and a few others. But I will only talk about squall lines and maybe generalize them to bow echoes. Now, what separates an isolated storm like these that we discussed before and squall line? Size. So for something to be a mesoscale convective system, in this case squall line, it has to have horizontal dimension in some direction, 100 or more kilometers. Okay, so the size of these clouds, of these thunderstorms, needs to be at least 100 kilometers in some direction in horizontal plane. And why is around 100 kilometers important? Because this is the distance at which the Coriolis force starts being important, which also means if you're studying these systems, you have to invoke Coriolis force. If you are studying isolated thunderstorms, most of the time, if not always, almost always, you can do analysis without considering the Coriolis force. So if we look into XY direction, horizontal plane, then a squall line might look something like this, where this now dimension, as I just said, is larger or equal, approximately 100 kilometers. Okay, and now in this direction, width, I guess, yeah, this is width, I don't know. Yeah, a few dozens of kilometers, okay. Now, let's take a cross section here across this squall line. Okay? If I take cross section across this squall line, then we can plot the flow field in the XZ direction. Okay? Now this is height Z. This is the surface of the Earth in the X direction. This storm, so this is squall line. So this storm in the vertical cross section might look something like this, let me think. As you can see, quite similar to multicell thunderstorm. So you can imagine really that squall line is like multicell thunderstorms arranged, in this case, in Y direction. There are differences that we will see now. There are differences. It's not that, but to first order of approximation, you can just imagine. So what would be a flow field in this squall line? Here we would have inflow that then spreads like so. Here is precipitation, and then here, this is all precipitation zone. here, which we will discuss, I will now plot it without explaining, but then I owe you explanation. In the mid-levels of this system, there is inflow into the storm, called rear inflow. Or also sometimes rear to front inflow. Because this is front part of the storm, the whole storm is moving in this direction. So this is front of the storm, this is the rear of the storm. And this is called the rear inflow. And above rear inflow, you have this updraft that is now spreading, forming this cloud over here. Here is precipitation, and again you have downdraft associated with precipitation, like so. Now I will indicate here, look, this is different type of precipitation from here. I will discuss this soon. So over here, right next to updraft, we have what is known as convective rain precipitation. And I'll discuss what it is. And then over here, far behind, we have stratiform precipitation. And between them is transition region. So what is convective precipitation? Convective precipitation is very intense localized precipitation, very intense rain formed by this strong updraft, but not as strong as supercell, but strong updraft creating very large hydrometeors, very large precipitation particles. And because these particles, rain or hail, are so large, they cannot be moved to the back. So they fall right next to the updraft, creating very strong localized precipitation known as convective precipitation. Now, smaller precipitation particles, they are moved in the back of the cloud, and they gradually fall down, forming this stratiform precipitation, which occupies much bigger region, but it's not as intense as convective precipitation. And then in between these two, there is always some transition, not always, there is often some transition zone or even region without precipitation. Because it tends to be that heavy precipitation is here, light precipitation is here. Quite often there is nothing between. And nothing between means you either get some weak rain or no rain. Okay? Is this clear? So I would like to reiterate what I just said. So we have updraft that creates these overshooting tops, that penetrate into stratosphere because the updraft is so strong. This updraft is inclined, as you can see, it is also inclined, and part of it spreads in the back of the cloud. You see, this is also updraft, but it's inclined, so vertical velocities are not as strong as here, which means you get precipitation that is not as intense as that one over here. And then again, associated with precipitation zone, you have outflow that spreads, just like before, right? Outflow spreads, and up against this outflow, you have updraft feeding into the cloud. Typically, in squall lines, storm relative winds, and I'm underlining storm relative winds, winds that the storm observes, are usually towards the storm at all heights, typically. So winds that the storm is observing are usually towards the storm at all heights, usually. And that is what is causing this region over here being spread so far away behind the top. Okay? These types of squall lines No, any questions online? Or here? These types of squall lines, now I will go back to XY. I will just replicate this figure that I already have. These types of squall lines are known as trailing stratiform because this region over here is that. This region is that. This region is this. Okay? So these are called trailing stratiform. Why are they called like that? Because this region over here is known as stratiform clouds. You can see that this over here is wider than thicker. And I said these are stratiform clouds. So stratiform clouds are trailing behind convective clouds. Okay? Approximately 80% of all squall lines in mid-latitudes are these types of squall lines. About 10–15% are leading stratiform. Leading stratiform would be, this is convective region, stratiform layer is like so, and the cloud is moving, the whole system is moving like that. Here the system is moving. Now you can see that in this case, the storm relative winds exactly would be away from the storm. But that's not common in mid-latitudes, so they are only about 10–15%. And we have third type. Third type is known as parallel stratiform, where convective region is like so, and then over here we have stratiform clouds. So this is stratiform, this is convective. In this case, you can see that storm relative winds are, if the storm is moving in this direction, storm relative winds at higher elevations are parallel to the axis of the storm. This is also 10–15% of all cases. Yes.
Because I understand this mechanism. If I mean, we're considering we're talking about something that is 100 kilometers. So
yeah,
how can a wind that is blowing exactly there reaching?
How can, but it has strong.
I understand because we say that it's a couple, 10–15 kilometers because we're considering the cross section.
Yeah.
But in the other case, the last one, we're considering something is much longer.
Yeah, so you take cross section here. This part looks the same, but this part, because storm relative winds are into the blackboard, this part is into the blackboard over there. So storm relative winds close to the surface are into the storm, but then as they ascend, they don't go back, they go into the blackboard.
Oh, okay.
And then this stratiform region is not trailing, but it's, we would say it's called parallel to the direction of motion. Whereas here, storm relative winds are at higher elevations, are in the direction of motion. So you get updraft that doesn't go back, but it spreads ahead of the storm. Okay? But again, if you study, now how do we know these are 80%, these are 10–15%? You cannot theoretically, this came from measurements. People did so many radar studies, and they figured out in mid-latitudes, wind directions with respect to the storm are such that you mostly get these types of squall lines. Now, I need to explain how do we get rear inflow. And there is no easy way to explain it, okay? There are two ways of explaining the existence of rear flank inflow. Let me just bring you back if this is surface of the Earth, this is height Z. Let's say wind is increasing with height like so. I mean, we calculated vorticity. You remember we got something like this. Okay. Now, if you have updraft, let's say here is cloud. Updraft is the strongest in the middle of the cloud. And then as you go to the edge, you get weaker updraft. So if you do that calculation for your homework, you will see that vorticity that forms here is like so. And this is also, you can imagine that this is moving faster than this. So it gets rotated like that. Is that clear? Because if this is clear, then we can kind of explain the real Planck inflow. In the following, that's one way of explaining it. Here is the surface of the Earth. Here is that cloud. That I plotted before. Here is the base of the cloud. Here we have updraft, and this updraft goes like so. Here is the strongest. This is still called updraft because maybe this should be a little bit inclined. Okay, it's not as vertical as this, but it's still inclined. It's weaker over here. Okay. Wind is weaker in the updraft, wind is weaker here, yet weaker here. Just like in this updraft, as you are moving away from the updraft, wind is decreasing. As you are moving away from this updraft, as well as here, winds are decreasing. So you get vorticity that looks like that. Now, at the same time, you remember, I told you there is precipitation here, everywhere here. This precipitation forms outflow. And in this outflow, you have vorticity like so. You have vorticity like so in the outflow. So you can see when you couple these two vorticities, they result in the inflow going towards the storm like that. That's one way of explaining the real Planck downdraft using just dynamic argument, vorticity argument. It's the vorticity generated by the shear in the updraft in the stratiform region and vorticity monoclinically generated in this outflow over here. The stronger the storm, what you said, the more energy, the more K the storm has, the stronger the outflow, the stronger the inflow. So there is correlation between buoyancy of the storm and the strength of this rear inflow. Okay? Is this clear conception, what I plotted here? So you have downdraft that spreads. Here you have vortex due to monoclinic generation. Here you have vortex associated with the shear in the wind. And they couple producing a rear inflow. Now, there is another way to explain it. A little bit more, maybe satisfactory way of explaining it. Because it turns out, you see, above this downdraft is the region of low pressure. And because this is low pressure compared to somewhere here, you get inflow. Let me first say this. If you trust me that here is low pressure, do you see how this comes? Online people, if you, and I'll demonstrate this is the case, but if you take for granted, if you trust me that low pressure is here compared to outside, then there will be pressure gradient force acting like so. Now I owe you to explain why would there be low pressure here. You don't have to think about it because it's not so simple to reason, okay? Again, in the course Mesoscale Meteorology, when I teach, there is a lecture called Pressure Perturbations. Or pressure perturbation equation. You take Navier-Stokes equations that we didn't derive, we stated in the first lecture. So take Navier-Stokes equations and then do divergence. And then do maybe 45 minutes of derivation and neglecting all terms, and you will get this equation. P prime, pressure perturbation. So pressure is average pressure plus perturbation. Okay? Pressure perturbation is proportional. This is strain rate, EIJ squared minus 1/2 omega squared minus delta B delta Z. I'll say what this is. This is vorticity that we defined before. I will not ask you this equation, but I want you not to trust me that there is low pressure here, but please demonstrate using equation. This is vorticity, and this is therefore intensity of vorticity. This is a very important equation because it tells you in the center of any vortex you don't have low pressure. Any vortex you create here, you have low pressure in the center because this is negative pressure perturbation. And this is always true, except not always. And this is not true when you include Coriolis force. As you know, Coriolis force, you have anticyclones, high pressure in the center. This is great superiority of atmospheric sciences over engineering, because in engineering, people always think vortex, low pressure in the center, and that's true. But this derivation assumes there is no Coriolis force. If you add Coriolis force, then you get some term that says sometimes you can have high pressure. This term over here is rate of deformation. So this is 1/2 sum over I goes from 1 to 3, J goes from 1 to 3. I will write this, but you don't need to know it. Delta UI, delta XJ plus delta UJ, delta XI. This is deformation. This is also a very important term because when I blow on this desk, I create spreading downdraft. Why is downdraft spreading? Because if you imagine from my mouth, parcel of air having this shape, as it is hitting the surface, it is deforming. Namely, it is deforming like that. And this says any deformation is positive pressure perturbation. So that means when I blow down, I'm deforming air parcels, creating high pressure, and therefore you get outflow spreading low. But there is this term as well. This is vertical change in buoyancy. Look, this is the key now. I'm here in cold air, going into updraft that is warm air. Cold air going into the cloud that is warm. So delta B, delta Z is positive. Right? Buoyancy is increasing with height here. And because of that minus, I get P prime smaller than 0. That's negative pressure perturbation. Where is the largest negative pressure perturbation? Right above this cold pool, because that's where you switch from cold air to relatively warm air. And therefore you get P prime negative pressure gradient force twice the equivalence. So these are two explanations of real flow inflow. One is using pure dynamics, shear. Another one, you have to know this equation, but I'm not going to ask you to memorize this equation. We usually derive this in Mesoscale meteorology. It's not, this is how you do it if you want to do it. And you'll see how to do it in the literature that I provide here. Any questions about this? But I hope if you trust me that this equation holds, and it does, then you can understand how this works over here. And last 3 minutes, I would like to say a few words about both echoes. You see, this is squall line. This is squall line. We assume it's moving from east, west to east, from left to right. And we saw this rear inflow. Where is the rear inflow the strongest? It turns out it's the strongest in the middle of the system, because the edges of the system are where the system died. I mean, this is the end. So the strongest rear inflow is here in the middle. And then consequently, in the next moment in time, if this is T0, in moment in time T1, this whole system might start looking like a donut, like a ball. Because the rear inflow is favoring the middle of the system, whereas the end of the system starts curving in, like so. Is this clear? Now, I should also say, these rear inflow jets, when they reach the surface, they create extremely high winds. Fujita also called these downbursts. So you saw in that conceptual model, this rear inflow was like so. It doesn't always, but sometimes it reaches all the way to the surface. When that happens, you get very high winds, because these are winds from several kilometers in the atmosphere descending towards the surface. And therefore, the strongest winds associated with bow echoes are quite often here at the apex of the echo, because that's where this rear inflow is the strongest. And then you have these curling in vortices, because now from a straight line you started having bow, so you have, if this is northern hemisphere, is this cyclonic or anticyclonic circulation? I know you're tired, this is the end. But okay, this is cyclonic circulation, counterclockwise. This is cyclonic. And over time, because again, these are hundreds of kilometers, so this is much higher, well, higher latitude than this. This one dominates because Coriolis force over here accumulates much more than over here. So you get at the end, you get this coma shape quite often. Where you now also quite often have severe weather over here as well as over here. This may be in time T3. So you get from squall line to bow echo, like so. And sometimes here you have trailing a little bit of cloud from the, because here you constantly get formation dissipation of this end, of this anticyclonic, where cyclonic straightens because it's at higher latitude. So here are strong surface winds. So you can see that this rear inflow plays a crucial role in the development of bow echo. So what is bow echo? Well, it's a squall line deformed by the strong inflow at the rear that creates something. And lastly, one sentence, maybe you heard for derechos. Derechos are bow echoes that are exceptionally strong. There is some technical classification that I forgot. If damage over 100 square kilometers is such and such, and it lasts more than 3 hours. So if you read derecho, which is Spanish word for something, derecho is bow echo that satisfies some technical requirement. Okay, that's it for storm. So we covered single cell, multicell, supercell, storms, which are individual storms, and we covered 1.5 types of systems. We covered squall lines, and bow echoes are basically continuation of squall lines associated with strong inflow. Any questions? Any questions from online audience?
Peso.
There is never any question from online people, so I'm wondering if they see anything here on these blackboards, or it's much clearer to people online compared to people in person. Okay, well, if there is no questions, don't forget tomorrow we have yet another lecture, and that lecture will be indeed on hurricanes. And then we don't have a lecture for 7-8 days or something like that. Okay? See you all tomorrow. Tomorrow it starts 3 p.m. like usual. Bye-bye.
Thank you. Bye bye.